Hello, everyone, and welcome to today's presentation, Storage Tank Inspection and Calibration using Trimble Laser Scanning Solutions. My name is Jason Hayes. I'm Product Manager for Geospatial Laser Scanning Software. And prior to this role, I was a Product Manager in our Oil, Gas, and Chemical Division, where I spent a number of years talking to customers around the world on oil and gas solutions, and in particular, spent a lot of time talking about storage tank and inspection, and taking the input that they gave me and refining our solutions for storage tank inspection and calibration. Now, a lot of you have probably seen headlines like this lately about the oil and running out of places to store it. Now, nobody really knows what's going to happen in the future, tomorrow, 6 weeks from now, or 6 months from now. But what we do know is that in the past couple of months, there was a lot of oversupply and at the same time, a huge drop in demand. So when we're making too much and nobody's using it, we have to find a place to store it. That's why you see headlines like this. It's put a lot of emphasis on storage of petroleum products, how we do it and where we do it. So it seemed timely to do a presentation on our storage tank solutions. Now, during this presentation, I'm going to make a few assumptions. I'm going to assume that most of you on this call are probably already pretty familiar with storage tanks and what they are. I'm also going to assume that most of you are probably familiar about your specific disciplines, such as storage tank inspection, storage tank calibration, and the standards in your local regions. Now, I'll briefly describe these at a high level, but we won't spend a lot of time dwelling on these aspects. Now, who this presentation is for: those new to scanning, but already know about storage tanks, either on the inspection side, the calibration side, or maybe you're involved with construction of tanks, or you're an owner-operator and you've got tank assets and you're curious about how the solution can be applied to them. It could also apply to those that are currently using laser scanners or employ laser scanners for facilities, management, or other aspects of your oil and gas or city maintenance or whatever, and you're curious how you can use your current laser scanner technology on storage tanks. Now, through the presentation, when I refer to storage tanks, you probably immediately think of oil and gas and petroleum products, but storage tanks could also contain water. We've even had customers using our solutions for wine and trying to apply it to beer. So pretty much anything that is a storage tank, you could use our solutions for. And then the third people, there may be those that are just new to scanning and new to tanks, and they thought this would be a great way to spend Tuesday. Now, for our agenda, we're going to go and look at what is laser scanning. Then we're going to go in and look at the benefits of laser scanning, how it's faster, cheaper, gives you better coverage, these kinds of things. We're going to take a look at our solutions. Then we'll go through how to get started in laser scanning. And then at the very end, we'll open it up for some questions. Now, as I'm going, feel free to go and type any questions in, and I can read through those at the end of the presentation, just so you don't forget before we get to the end of the presentation. Now, when we talk about what laser scanning is, it's commonly referred to as LiDAR, or light detection and ranging. And it works on the principle of having an instrument with a laser source. You send a pulse out to an object, and you'll time how long it takes that pulse to come back to you. So knowing the speed of light, how long it should take to move, you can figure out the distance. If the instrument is also turning angles, horizontal and vertical, you can pinpoint an exact X, Y, Z, or northeast elevation coordinates on that surface. Now, a total station will generally take about a shot per second, depending on what you're doing. Then you'll move somewhere and take another shot, move somewhere else and take another shot. So probably a shot every second. Laser scanners, on the other hand, they'll take a single point measurement, but they're doing this very rapidly. So in 1 second, they're not taking one shot, but they're taking millions of shots. Now, because it's going so fast, each individual shot may not be as accurate as a single total station measurement. It could be a little bit like a millimeter or 2 millimeters one side of the object, or a millimeter or two the other side of the object. And certainly some of the returns of that pulse will show up being right on the object. The big difference is with scanning, you're going to take the average to find where the true object is instead of relying on one single point. Now, because of that, standards haven't been written specifically for laser scanners yet. They've been written for total stations and trolleys and measuring tapes, but laser scanning, they just haven't got around to writing standards for these yet. The main point here, laser scanners, although very similar to a total station, are actually quite different in how they're operating. Once all of those points come back, you'll get what you see here. This is a point cloud, so a collection of those hundreds of millions or billions of points that you can then work with on your computer. You can view it with different renderings depending on what you need, take measurements, and do a lot of different analysis on this. Now, to compare that to traditional methods, say a total station, where you'd set up and you would take individual shots on the point or on the tank, such as this, you would start out with vertical inspection stations. You can think of these as mile markers or kilometer markers to let you know how far you've gone on the road. On the tank, you would start with a single vertical position, and then you would go counterclockwise or clockwise in even increments. So a small tank may have a minimum of 8. As you get larger tanks, they may go up to 10, 12, or several dozen, depending on the size of the tank or the client's request. Once you do that, then you'll start to take horizontal measurements, getting the circumference of the tank, and you'll start measuring near the bottom, near the shell to bottom weld. So you'll measure near the weld, and the way the tanks are built, if you can look here at the image, you'll see these kind of tiers like a wedding cake, where you'll build a tier at the bottom, and then you'll move up and build another tier, move up and build another tier, and so forth until you get to the top. These are known as courses from one weld to the next. So when you're taking your measurements, you would generally measure along the bottom, then you measure just slightly above the bottom weld, and then you might measure in between each of the welds, and then below the top weld, and then you'd repeat. You'd go above the bottom weld, or above the weld, in between, below, above, in between, and below, until you get all the way to the top of the tank. Then you would look at the measurements where all of these intersect, the vertical lines and the horizontal lines. And you would end up with a number of points. And in this case, this tank had about 200 points in total. But when I look at this image of the tank, the way the light is hitting the shell, I can actually see some deformations just visually looking at it. The interesting thing is when I look at these deformations and where they are, they're actually falling where there's no green measurements. So no measurements have been taken on these using a traditional workflow like you would use with a total station. The fact is, you're missing a lot of area when you're just taking samples of the tank. Now, in the past, it's been cost and time prohibitive to measure every single inch of the tank. However, with laser scanners, you can see we can now cover every single part of the tank in great detail. And by capturing all of that information, it then now allows us to go in and do analysis. In this case, I've compared the tank to a perfect cylinder. You can also compare it to a design. So if you're doing storage tank and construction, you could scan as you're doing each course to make sure that nothing is getting off while you're building the tank and that everything's going to align in the end. You can see here that the two areas with these kind of bright blue colors kind of line up with where I had circled that I could visually see those deformations. So this gives me that confirmation that there is in fact something going wrong. We've also got additional visualizations where we can do an in or out or a cut fill, if you will, of what's going on. So the blue areas, the darker the color is, the more the tank is bent in, The dark red out areas are where it's bent out. So you can see here, in fact, we have dark blue right next to dark red, meaning there's a lot of deformation going on in those areas. And that's what people are going to be looking for when they're considering if their tank needs to be repaired or is fit for service. Now, looking at our solutions, we start out with data capture. So this is done with one of our 3D laser scanners. This is one of our newer scanners that we've put out. You'll move around the tank, capturing the scans. Now you can put these scans together to make a full 3D replica, digital copy of your tank. And you can put these together either by using the point cloud itself or using targets such as black and white checker targets. You see a couple of these on the tank there. And the way it works is you'll start out by capturing one scan, then the next, then the next, then the next, until they all come together to create a final 3D replica of your tank. Now the instruments that we use, this is the Trimble SX10 scanning total station. And the reason people like to use this, we've got a number of them I'll go through. This solution is used because while it's not what we would commonly refer to as a full-blown laser scanner, it has a few other great attributes. One, it's a 1 second total station. So this is a great total station. And remember earlier when I said that standards hadn't been written specifically for laser scanners yet, this shows up specifically in the API NPMS Chapter 2, 2.2D specifically, that calls out standards for laser scanners and doing volume calibration, or not laser scanners, total stations for doing volume calibration on tanks. So even though it's not a full-blown laser scanner, that works in its favor because it's a total station with scanning capability, meaning if you wanted to, you could probably use it for doing volume calibrations, meeting probably API and ISO standards. In addition, it's got very small spot size, so it gives you very high accuracy individual measurements. DR mode is called measurements without using a target, a prism target you would traditionally use with survey instruments. Also creates a very low noise point cloud, and it has the ability to traverse around the tank using survey methods. So if you've got a survey background or you're familiar with survey methodology, this is a very easy instrument to use and to understand because it uses those workflows. And because it's also a total station, you can carry a measurement rod out in the field with you, a prism, and you can take hard to get measurements. So you can imagine a lot of grass growing around your storage tank. And the way laser scanners work is line of sight. So if grass is in the way, you can't see the ground. But with a prism rod, you can go and stick it down in the ground or in the water. A lot of the tank facilities here in the U.S. are located around the south where we get a lot of precipitation, a lot of rain. So you have water standing because you have these secondary containments built around the tanks to hold liquids in. So laser scanners, because they're light, they can reflect and do weird things when they hit water. So having a total station will allow you to get some shots in those difficult areas as well. And it also has the ability to only scan what you need because you're using a survey traverse to register all of your stations together. You don't have to rely on overlapping point cloud data, which means that you can scan small areas. So even though it doesn't have the high speed of what we would refer to as a full-blown laser scanner, you do get some time savings in that you can scan small areas. And the cameras inside the SX10 are great and provide very high resolution images with a great zoom as well. And then finally, it's one instrument, or it's two instruments in one. So you get the total station and the scanner. So it's great, especially if you're doing storage tank construction. The example I gave you earlier, maybe you do find an area that is out of tolerance or not meeting the specs. You can use the very same instrument that you use to capture the data to then go and stake out and locate where these areas are. Now, in contrast, we also have what we call the full-blown laser scanners, the Trimble TX6 or TX8. Now, what makes these so appealing is these are very fast scanners, up to 1 million points per second. And they also have a survey-grade compensator. Now, not all laser scanners have the same survey-grade compensator. Now, of course, all of the three that I'll show you here do. Many scanners can just have a compensator similar to what you would have in your iPhone, which isn't great. And if you're checking verticality on a tank, it's very important to have these survey grade compensators so you make sure that you know what true plumb or true level is. In addition, these also provide a constant range noise over the full range. Earlier, I showed you how laser scanners would scan that wall. Some of the points would be right on the wall. Some would be a little to one side or the other. Some laser scanners work on a principle that allows for very high accuracy up close, but as you get farther away from the scanners, that range noise starts to increase, and sometimes very quickly, so that you get a very noisy point cloud. With the TX series, it's going to have a constant plus or minus 2 millimeters out to almost the full extent of the scanners. And they also allow for an area scan. So the way these work is they'll do one 360 scan, capturing everything around them. If there's something far away or up high on the tank that you want more density on, you can segment or select just that area and then do a high density scan in that specific area. Now, the newest scanner that we've added to our portfolio is the Trimble X7 with perspective software. So the scanner is controlled using a ruggedized build tablet and provides reliable workflows for all users, whether you're experienced or just getting started in scanning. This is in part due to the perspective software being very intuitive and easy to operate. One thing that's prevented people from getting involved in scanning has been, well, first off, the price. The scanner has actually got a very good price. But after that was just being intimidated, getting involved with learning a new system, a new technology. We put great efforts in this system to make it very easy to operate and understand what's going on while you're in the field. The scanner is also compact and lightweight, which makes it great. Many scanning professionals are located in one place, but the tanks they need to inspect or calibrate are located somewhere else, which means they're getting on a plane and flying there, which means you either have to ship your scanner, which is time consuming and a little scary because you don't know what the delivery people are going to do to your scanner, or you can check it and carry it on the plane, where when you check it, you don't know what the baggage handlers are going to do with it. If they treat it the way they treat my luggage, it's going to be in bad shape when it gets there. So having these small form factors allows you to put this scanner in the overhead bin and carry it right with you on the airplane. It's got a few breakthrough innovations for reliable data collection. One is auto calibration. I talked about traveling and getting to a site. When you get there, even things that are in the overhead bin, I know before I've had mechanical equipment with me and it's been in the overhead bin, and when I opened it, all the screws fell out just from the vibrations of flight. So you never know what might happen while you're in transit. This scanner will run an auto calibration routine before the scans to make sure that the data is going to be as good as possible. So it gives you peace of mind that when you get there, it's not just going to tell you if it's in calibration or out, it's actually going to apply a calibration. It also has an automatic survey grade leveling. So another intimidating thing about scanners was trying to spend the time to learn how to get them level on a tripod. If you didn't have a lot of survey experience, this could be time consuming. With this scanner, you just need to get it close, and then the scanner will take over and finish on its own to apply this leveling compensation. It also has a high sensitivity EDM, that's electronic distance measurement mode, that helps to capture dark and reflective surfaces at distance. So many times when you're going to a storage tank, it may still have product caked onto the sides or inside, which would typically be difficult for a laser scanner to get these dark surfaces. This high sensitivity mode helps you in those situations. And it also offers flexible operation, so you can use it with the tablet or without. So maybe you're already a very skilled in scanning, and you don't need the in-field visualization of the data or the registration to let you know you got everything and that it's right. And you don't want to carry the tablet, you can just push the button on the side of the scanner and it will do the scans for you as well. And of course, the data integrates well with Trimble and non-Trimble software. So for example, if you just wanted to take this data into, say, AutoCAD or Autodesk, you could export it straight out of the tablet and go directly into there. And lastly, it's also got an unprecedented 2-year warranty, giving you peace of mind that you've made a great investment. Now, there's 2 parts to working with storage tanks with laser scanning. There's the field data capture, which I just described, and then there's creating deliverables and getting information and meaning out of your scan data. And that's all done in the Office software. The Office software that we use is Trimble RealWorks Advanced Tank. Now, this is a software that's used specifically for laser scanning, and this edition is made specific for those in the storage tank industry. It handles all of the registration, putting each of those scans together for you, whether you're using targets or no targets, so you have flexibility to work however you like. It also has the ability to go in and classify the different components of your tank, which I'll show you a little bit later. Huge time-saving benefit there. It allows for tank inspection, calibration, evaluation of the secondary containment. Also has modeling tools and other analysis tools to go in and analyze your tank. Now, the software, when we're talking about doing storage tank inspection, most of the automated tools are applying to vertical cylindrical storage tanks, like you see here in the top, or horizontal storage tanks like you would find in a rail tank. When I talk about the classification earlier, the first step is to go through and let the software identify automatically the different components of the tank. So for example, identifying the roof, the shell, the floor, the deadwood being anything inside the tank that would subtract from the volume, and then identifying everything else that it doesn't know. It could be equipment or people walking around in the tank that needs to be removed before you can do your analysis. Now, this is something that could take days in the past before software was developed specifically for storage tanks, tediously going and removing sandblasters and air compressors and trucks and weeds and grass and spiraling staircases, and all of these things could be very tedious. The software has got this down to be a very quick process. Now, when we talk about next is tank inspection and tank calibration. I have no idea why I get these news updates here. Tank inspection is the process of going through and visually and electronically determining the physical state of the tank and its environment. So you can imagine if you were to buy a new house or a new car, you would go through and inspect it. You would make sure there were no dents, that there was no rust. You'd look at it visually. You might take it to a mechanic to get inspected. Same thing with storage tanks. You want to go through and make sure that these things are sound and ready for use and for a long time. Tank calibration, on the other hand, is the process of determining the correct volume of a substance that the tank can actually have, going for different measurement marks. These are 2 things that we address within the Trimble RealWorks software. Start out by looking at the inspections. Now, a lot of the benefits of using laser scanning for storage tank inspections is that it's reducing the field time. Typically, one person can go out and scan a whole tank within an hour. Now, certainly if it's a gigantic tank and you need a lot of extra detail, it could take more. But if you're able to get inside a tank, scan inside, see the bottom, the shell, the roof, you can do this very quickly and easily with a laser scanner with a single person. As we saw earlier, you get detailed, accurate data on the entire tank. So the laser scanners can see this down to very, very close spacing on these points, so nothing is missed. Also, like I showed you earlier, it provides this great visualization with different tools being able to highlight different areas or problem areas with the tank. And it gives you that complete verticality, complete roundness, and as well as complete shell settlement and any distortion analysis, and allows you to take any of these measurements from the safety and comfort of your office desk. Now, when we look at the storage tank inspection, we'll go in and look at setting up the tank. So you can see it's using terminology and workflows familiar to those in laser scanning, such as defining storage tank, such as defining your courses, adding, removing the position of welds. It's all in very easy step-by-step. You see step 1, step 2, step 3 to go in and measure these tanks. Then you will go through and create ultimately a verticality report. Now you can see here, this is kind of an amalgamation of talking to many involved in the industry, creating a report, trying to fit in most people's needs. Everyone has slightly different ways of doing their reports over the years, and we've tried to incorporate as many as we could. On the left side here, you'll see the graphical representation of the tank. You can imagine the tank overlaid here and cut in half. These are those even intervals, so you imagine like slicing a pizza. So you see station 1 on the left side. The middle, where you see that orange line, is the theoretical perfect tank shell that would be vertical. The green lines are the tolerances that we've set within the software. And then the blue line that's kind of zigzag and has the nodes, that's an exaggeration of what the tank shell is actually doing. Now, again, we exaggerate it so it's easier to see what's going on and where areas are getting out of calibration or out of tolerance. Now, on the right side, you see the station opposite it, in this case, station 5. And you can see that most of that is all within tolerance. One area on course 4 is just about to get out, but it is within tolerance. Whereas on the left, you see on station 1, several areas getting out of tolerance. Now, on the right side of the screen, you see the same information displayed in a table form. So this is all data you can copy and paste into a spreadsheet. I know most people doing tank inspection or calibration have created spreadsheets over the years that they use. This data, you can just copy and drop it right in if you want to use something you're more familiar with. And then at the bottom is a comparison to perfect cylinder, so you could see what was going on at any place on the tank, whether it's tilting in or it's bulging out. In addition, we also generate roundness reports. Again, this should look fairly familiar to most of you. You can imagine the tank center here, the perfect round tank in the middle, with the green lines being the tolerance values that we've set. These are all customizable, so you can enter whatever tolerance values you want to meet whatever standard you're trying to meet. And then, of course, the blue line going around is the exaggerated view of what the tank shell is doing. So you can see up at the top of the screen, the blue line's getting just outside of the green tolerance values. And then if you look at the table down below, you can see, in fact, that at that position, we are failing. Now, another thing that's of particular interest to inspection and construction is the settlement, the edge, and being able to look at this and know what's going on over time, because you've got all of this weight pushing down on the outside of the bottom of the tank. These shells are quite heavy, and they'll certainly start to bend down slowly over time, or have the potential to. But what you don't want to have is, if you look at the graph on the right, an area where it's bending too sharp, too close, and this will typically happen close to the edge of the shell, where the bottom meets the shell, and that could cause problems. So we've got tools that allow you to go in and analyze this. Now, traditionally, you would probably start with a laser level or something, and you would have somebody with a level rod with elevations on it, and they would start out at the tank edge, and they would start working their way towards the center of the tank. Now, taking the measurements very close together at the outer part of the tank, because that's where you're going to run into these problems, and then moving towards the middle of the tank with a bigger spacing once you get to the middle, because you're not as worried about having this problem of the shell pushing down in the middle. So because of that, on the outside, you have many close measurements. If you see the green dots in the lower left-hand corner, and then as you get closer to the middle of the screen, or the middle of the tank, you can space these measurements out a lot farther. That's how you traditionally do it. Of course, with laser scanning, you'll see all of the bottom. But we also have tools that allow you to analyze the entire bottom. So you can see here in this screen snap, we've got the evenly spaced inspection stations going around the tank, but we've also done that analysis where we look at a perfectly flat floor, and then we compare it to the point cloud to see, now it could be flat, it could be cone up or cone down. Let me make that clarification. If there's any extra deviations that aren't on there. So in this case, we found some areas that are maybe falling in between those regular inspection stations. So we're adding an extra row of inspection there so that it will show up in our report. Now, when we create our reports, you can see on the left side, just going to move my mouse, you can see we've got many stations starting here along the shell. And as we move towards the middle of the station, the middle of the tank, as I mentioned earlier, the spacing on these measurements is a lot farther. Now, the reason we have these like this is we know most people are familiar with looking at traditional tank inspection reports. So we're handling all the traditional ways of viewing it and the way the standards are built. And in addition, we give you these extra tools to go in and analyze and look at the entire tank surface, the bottom or the shells, so that you can make more decisions. So just to make that clear, we're trying to follow the standards, API in particular, as close as possible, knowing that you'll also use additional tools to get the maximum value out of your laser scanner. Now, when we look at the tank calibration, we've got a separate set of tools for tank calibration. Within these tools, you can see the UI here. You'll go in, define the position of the dipping plate by picking a point, or you could do a best fit flat plane to these dipping points, these dipping plates. You can also go in, define the maximum level. You can type in a value, or you can physically click on the point cloud of the tank to define this. And then you can set an interval. You could think of these as virtual strapping, how often you're going to check the circumference of the tank, starting at the bottom and moving up, starting at the dipping plate and moving up to that maximum level. Then we'll also calculate below the dipping plate. That will all be considered the sump area. We'll create a volume on that as well. Now, we do have the ability to enter a shell thickness. However, we're not so sophisticated that you can put in different shell thicknesses. I understand that you'll have different thicknesses as you go up the tank. In this case, you would probably have to figure out an average if you wanted to do this. This would only be considered if you scanned the tank from the outside. We would assume most people doing a volume calibration would be scanning from the inside, in which case you really don't need to worry about the shell thickness. It would only be if somebody wanted to scan a tank from the outside to calculate the volume. Now, once you've done and you've got all of your virtual strapping done, this simulates wrapping a tape around the tank. You get the true circumference at each of these intervals going up the tank, and you saw that those were custom defined. Then you can go through and inspect each one of these to make sure that they've extracted properly. Again, the software tries to do as much as it can automatically, but it tries to err on the side of caution, so we don't want to do something wrong. So everything has the ability to go through and manually inspect what's been done automatically. and make any changes if you need to. So in this case, you can see on the right all of the different sections that have been created. We can just click on the arrow to go through each one and just visually check to make sure that that line is actually following the tank shell and didn't miss a hole because of a manway or something that needs to be filled in, or to maybe we didn't do a good job cleaning and we missed a nozzle or something, and it virtually measured over the top of that nozzle. So you can go through and check each of these. Once you do that, you'll export out a strapping table, which can then be brought into another application we have to create your tank calibration report. So once you import that strapping table, here's the parameters for importing that. It will populate each of the fields, and then you can go through and set all of your compensation values and then create parameters for how you want your calibration table to be created. And it can interpolate between each of those intervals. So the nice thing with laser scanning is you can actually create those strapping intervals as close as you want. It's no more effort than to do 100 than it is to do 2, really. You just type in how many intervals you want it to do. But once we create the capacity table, we then can even further define the filling table intervals that we want on here. So in this case, it looks like we've done one every inch. Now you could set that to be pretty small. I think I don't remember the smallest value, but it's pretty small, probably less than a 1/4 inch. So ridiculously small. Now I will tell you that when we calculate our filling tables, this is based on an empty tank, not accounting for any dead wood. It's removing all of the dead wood, so that's not being subtracted from these. If you want to do that, you would do a mix of what we currently have with the automated strapping table. Then you could manually take all of the measurements again in your air-conditioned office where it's nice and clean and safe. You could fit pipe, you could measure any kind of support structures and get those measurements and then manually enter those into any other spreadsheet that you've been using over time. So even though we don't have the automation to account for dead wood or floating roof displacement, because these are pretty difficult things for the software to automatically figure out, especially for scanning, because so much of the dead wood could be heating or mixing components towards the bottom of the tank, which is difficult to get the scanner under them. The human eye can look at them and measure them and know them, but automated is pretty tricky. The next thing that we look at is secondary containment. So if you're going to go and measure the dike walls, the earth walls built around a tank, or concrete walls, we've got automated tools to help you there as well. In this case, we've got tools to automatically clean the ground to remove vegetation, people, vehicles, equipment that might be parked out there temporarily to get down to the bare ground. Then you'll define the area of this boundary that you want to calculate the volume for. You then can create the criteria that you want for a report, and you can enter in rainfall parameters as well. Most of these tanks, when the secondary volume is containment areas are created, they need to account for a heavy rainfall that could happen at the same time that a tank would fail. And then you'll get a report showing the volume area, how much it will hold, and displayed as a percentage of the tank. In this case, it would hold 58% of the tank. The software is automatically looking at the tank and extracting that. Now it's not an exact measurement. It's basically looking at the bottom of the tank and the top of the tank, creating a cylinder and creating that volume, and then adjusting the volume of the containment area to that. Now, I will mention this tool is only working on one tank in a containment area. If you had a containment area built to contain, say, 4 or 8 tanks, you need to run this multiple times. Now, in addition to the automated tools, we have several semi-automated tools that will allow you to go in and do inspection. In this example, looking at the support structures inside a tank, maybe it's being retrofitted or upgraded to be a floating roof tank. you need to make sure that everything is fitting, or maybe during tank construction, you want to go in and make sure everything is aligning perfectly. So on the right, you see that I've created cross sections of the tank and then displayed them in unique ways. So on the left, you'll see one vertical support, and you can see that we've taken a check on it every 1.5 meters. Then if you look in the middle part here, you'll see each of those rings is what the tank is really doing. And in the middle is just a reference of where the true center of that support structure is at the bottom. So you can see that it moves in different directions. It starts out being, dead center at the bottom on the support structure. Then it starts to meander and go down towards the bottom, and then over to the left, and then starts to twist around to the right. These are kind of hard to describe to engineers, right? They just say which way it's leaning. You need to tell them, well, at 1.5 meters, it's starting to go north. And then at, 3 meters, it's starting to go north and east. And then maybe at 9 meters, it's going south, southeast or something like that. On the right, you can also see another visualization. So that's the beauty of 3D and having all of the data. Makes it really clear to be able to go in and look at these tank structures and see exactly what's going on and where, so you can make informed decisions on how to go back and make repairs or adjustments on your tanks. One more thing I'd like to mention, in the Trimble RealWorks Advanced Tank Edition, you also have all of the modeling tools available. So I used part of those in that last analysis for the structures. If you're doing other facility type work, we've got tools such as these automatic pipe extractions or manual pipe or cylinder modeling, so that you can model your entire facility. So if you're looking at upgrading or renovating, or maybe you just have no idea about any of your assets, laser scanning is a really quick way to capture the entire facility, including all of your tanks, and do analysis on all of this. And it's all in one package. Now, one interesting thing, I've been talking about laser scanners, but a lot of the inspection companies I've been talking to have started to employ drones in their inspection and creating point clouds from their drones and then doing quick calculations on things. You can bring the point cloud data from pretty much any source into Trimble RealWorks. It can be handheld laser scanners, the full-blown laser scanners like I've showed you here, point clouds from photogrammetry or drones. So it's very flexible in the way it can work with your data. And then finally, you'll want to probably share this data. You'll give your clients the reports for sure, but many of the clients have seen the beauty of laser scanning and the benefits of having these whole tanks as a digital copy on their computer and being able to share those with their engineering teams. So they've been asking for the point cloud or representations of the point clouds that they can use in addition to their reports. On the left here, this is an example of creating a published project using what we call Trimble Scan Explorer Viewer. It allows you to create a self-contained kind of viewer report, if you will, where you can add in media such as documents that could be all of your reports. You can add in images. You can add hyperlinks to web pages or email addresses or to other documents. You could even bundle in CAD projects and have links to those. So if they had the right software, they could open those. And then you also have the option to go in and put your own company logo and the ability to extract the point cloud. So they can look at this nice view like you see here on the right with annotations or add annotations. But if they wanted to, they could extract the full 3D point cloud out of there. It's up to you if you want to give your client that ability to extract that out. And you can also change the size of the file. So if they just need some of the points, you can keep the file smaller. That's what you see on the left where it says data file size. And it makes a really convenient way to share the data and what's going on. You can also, on the right, as you look through there, we call it a station-based view. It's very similar to like a Google Street View, where it's kind of the first person view as if you were standing there, and you can rotate around and look, take measurements, add annotations, etc. So how to get started? So if you're looking to get started with this, start out by going to our Trimble website for storage tanks. You can do a screen snap of the link there, or you can just go to trimble.com and find it under our solutions. Me, I just type in to Google Trimble storage tanks, and it pops up at the top of the list, and I click that link to go there. Once you get to the website, it's got all of the information you could want on storage tank solutions. It's got all the information on all of the laser scanners that I've showed you today. It's also got links to all of the information about the software, as well as specifications, system components. Also at the bottom, you'll see news stories or testimonials, or different places that stories about our solutions have shown up that you can click on to read about or to watch videos on. And if you look at the top, there's a button that's called Where to Buy. Oh, sorry, there's a contact button. So there's a contact button on our webpage, and then that's where you'll go to find. Certainly, we like to sell things, and that's how we keep in business. But more than that, we like happy customers. I would never want somebody to buy something that they're not happy with. So I would make sure you reach out to your local dealer and set up a demo. Say, hey, I'd like you to come help me scan a tank, or you could rent a scanner for a week to try it out if you wanted to. But make sure you try the solution out and make sure that it fits your needs for what you want to try to do. Then you'll want to request a 30-day trial license for Trimble RealWorks. So you can go through and try it. Your dealer will be able to give you training, get you started on that. If you don't want to wait, you can also go to the official TRW, that's Trimble RealWorks YouTube channel, where you can watch training videos on how to get started with the software, doing the import, the registration, step by step, how to do analysis on the point clouds, and as well as videos on the storage tank solution. So in summary, we have a very efficient solution for tank inspection and calibration. It greatly reduces your field time. As I had mentioned earlier, a single person can scan a tank most times in less than an hour. If they get really big or you want more detail, it may go to a couple of hours. The software, the automation in it is really key. In the past, I would talk to customers and they would be spending up to 5 days going through and trying to work with scan data to create results. These were before a storage tank specific solution existed. They've been able to drastically reduce that amount of time. And as well, there's also opportunities then to expand your business. So if you already have a scanner, you're already scanning your tanks, you can see that there's areas to move out and start to scan more facilities. If you're just getting into this, you can see the benefit of using the laser scanner for a number of different areas. With that, looks like I'm right on time. I will open it up to any questions that you might have.
So the first question here is, what technology was used to measure the thickness of a tank?
So the first question is, what technology is used to measure the thickness of the tank? There are different instruments available that will allow you to go through and do measurements on there. If you wanted to use laser scanning, you could scan the inside and the outside of the tank. For example, if it was an insulated tank, this would give you a good idea. But there are special equipment designed specifically to go and measure the thickness of steel. I probably wouldn't rely on a laser scanner for very small steel plates to go in. I would use that other specialized equipment. Next question.
The next question is, what scanners would you recommend for elevated tanks?
What scanners would I recommend for elevator tanks? I don't know the best answer for that. Maybe if you could add a little bit more detail on your question. So if you wouldn't mind typing a little bit more detail about that. Next question.
Any easy way to integrate and spatially correlate data from corrosion and bottom wall thickness inspections? Also attaching pressure test reports.
Yeah, so I don't have direct workflows for those. There's a couple of different ways. If you have images or printouts from that, there are tools within RealWorks that will allow you to overlay photos on the point cloud or match them up to the point cloud, but we don't have specific automated tools for overlaying reports from other instruments on top of this, other than the image matching of those on top of there.
How do your clients accept the laser scan technology with respect to the API 653 standard?
Yep. So with clients accepting the laser scanners and the different standards, API 653 is well accepted for laser scanners. The standard doesn't really call out what measurement tools to use. It's more about what you need to measure and how you should measure it, and leaves it up to you which tools you would like to use. So that's pretty easy, and most of the people that I know using laser scanning are using it for inspection and using it to adhere to these API 653 or ISO standards, which are very similar. Where it gets a little bit muddy is when you start to look at the API MPMS volume calibration standards on the 2.2D for the electro-optical distance ranging method. I think I got that right, which is written primarily for total stations. Many people in the past have assumed that a laser scanner was identical to a total station, which through the presentation, I've told you that it's not. For example, in the standard for the NPMS, you need to take a target and then do what we call like a measure rounds, where you'll double your angles, sighting. So these are very intense survey, intense, very precise survey workflow methodologies that API has used. Because the scanners don't have this ability to double the angles and flop their barrels, you can't do that. So that means that you can't meet that standard. The tools we've written have tried to meet the spirit of the standard in every way possible, but because it's not written for scanning, it's not. And that's just on the volume calibration. Again, inspection, not too worried about that. People are jumping in. Even on the volume calibration, I know a lot of people are using laser scanning for their volume calibration. Some are claiming that they're meeting the API standards. Some don't even worry about it. It's a bit of the chicken and the egg with the API. They don't write the standards until people start to mass adopt a technology, but people don't really want to mass adopt a technology until there's a standard. So it's kind of the Wild West. I know a lot of people are using scanners today, not as many as are using it for inspection, but it's proven itself. We've had customers that have gone out and done hydro tests where they filled the tank, compared it to the volumes they get from laser scanning, and been very, very close. And of course, filling a tank with water is going to give you a very exact estimation of what the volume capacity is. And so they've proven it to themselves that they've very been happy. And I think that the API and maybe ISO are looking at this. I hear rumors that there's movement on writing a standard, but I also know it takes years to write these standards. So I know that was a really long answer to the whole solution, but just wanted to make that clear on laser scanning and standards. Inspection, I haven't seen any problem. Calibration, it's a bit of a Wild West there. All right, next question.
So I have here part of a question is, what is the accuracy and reliability of the data on the newer total stations and laser scanner like X7?
Yep, so the repeatability or reliability of the data should be good across all of them. Now, the accuracy and range noise is going to vary across the scanners. And that's why I say it's good to go out and get a demo and choose for yourself. So you can look at the data sheets or the spec sheets on the web page that I showed you there, and you can look through and see what you want for your requirements. The TX8 it's certainly going to have a very high accuracy, as it's a bigger, higher end scanner than, say, something like the X7. But the X7 has been quite popular with people and even other scanners, even though they're not at the highest level as the Cadillac or the Ferrari of laser scanners. So on that, like I said, just look at the data sheets and it will tell you every single number on there that you would want to know on the different scanning solutions. Next question.
So the next question is coming back to the elevated tanks. It says elevated tanks. What scanners would you recommend for elevated water storage tanks?
Oh, I got you. So in that case, it's going to depend. We don't have automated tools for spherical or oval shaped tanks, which many elevated water tanks are. But as far as capturing the data, any of them would work. The trick is going to be to getting the data on top. And that's where you get an accuracy question. Somebody had just asked. I know people are also using drones, which are a lot lower accuracy than a laser scanner. I guess that's arguably right. The drone guys might say differently. But to get way up on top, you either need to get a lift, a very high lift to be able to scan down on that surface, or use something like a drone. Now you could certainly mix data, right? You could use the full-blown laser scanners down low, and then use the drone on top. Now, if you've already figured out how to get lifts and scan up on top, then any of the scanners should be fine. But as far as range, the TX8 is going to have a longer range than the X7. The SX10 is going to have a crazy long range, more than you would ever need with a tank. But those are how I would approach that. Now, for calculating the volume, you could create cross sections or create objects and do that depending on the shape. If it's a vertical cylindrical shape, then the automated tools will work pretty well. If it's a sphere shape, you might have to do a little bit more manual work on that to get your calculations. Next question.
So the next question is regarding tank calibrations. It seems the only data that is averaged or assumed is the shell thickness for each tank plate going up the tank. Could one just use a thickness tester and manually test the plate thickness and then add this into the Trimble tank calibration software in order to generate a more accurate volume strapping table?
Yep. So on the tank shell thickness, on the end, if you scan from the inside, it's not going to matter. The scan data is going to be able to see physically where that surface is. If you're scanning it from the outside, like I mentioned earlier, you do have the option to enter in a thickness. Many tanks will have a plate on them stating the thickness for each course of the plates. But in our software, you can only enter in one thickness. So you need to average it out or something like that. Not sophisticated enough to put in a different thickness for each shell. Again, assuming most of the people were doing an interior scan to do their volume calibrations so they could account for deadwood and things like that. Later on, we got the request to do a scan on the outside. But yeah, you would need to get that information from somewhere. I wouldn't rely on just laser scanning data. You could find the tank records of when it was built to find out the thicknesses, or those tank plates, or like you said, use some other equipment to go through and do a test on those with like, I don't know, a magnetic system or something like that to get the thickness. But again, once you're done, you can only put in one thickness on there. Now, if you've got your own spreadsheet that you've created over time that you can account for these, excuse me, based on strapping tables, and you can certainly do that, but we don't have an automated way to do that for the different thicknesses on different courses. Next question.
Can we generate volume tables for spherical tanks?
No. The answer is, can you create filling tables for spherical tanks? No. That's a request we get time to time, but not common. So like I said, we're focusing on the vertical cylindrical storage tanks, not the spherical. So that's not to say that you can't scan it, take all the measurements that you would want to calculate it, but we don't have automated tools that will go through and do that.
Last question is, how long does it take to obtain all the reports for API 653?
It shouldn't take too long. So usually when I'm doing demos for people, in the course of an hour, I can bring the tank in, get it registered, and get a report out on the verticality and roundness. This goes pretty quick, getting the tank registered, getting it cleaned up, removing spiral staircases, appurtenances, nozzles, manways, and things like this, and getting that. Now, the detail of how nice you want your report to look, or how much information is requested. Do they want the bottom, the edge settlement, and all of these, right? That'll add a little bit more time. But the reports that I showed in the presentation, those all were created pretty fast, right? I think within an hour, I can get the automated tools to go through and create those. Now, of course, it's going to depend on how big the tank is. The larger the tanks are, the more data that you have to crunch, so they could take more time. But that's, like I said, a small tank, let's say a small tank where I've got 8 to, I don't know, say 16 inspection stations, I can probably do those in a matter of an hour, just getting those roughed in. And then, like I said, then it's how much detail you want to go in and add, or how much you feel comfortable going in and evaluating everything before you turn it over. And I can't answer that for everybody, but just getting the base foundation, it goes really quick. And I keep using the example of an hour because generally when I do a demo, I'll do an hour-long demo, and that'll be me bringing a tank in, registering it, classifying the different components, doing the cleanup, and then creating these reports like I showed you here, and as well as talking and answering questions. So it goes pretty fast. But again, bigger tanks, it will take longer to register, to put the data together, unless you're using something like the X7 where it's already registered in the field. So I hope that answered the question. I see that we've gone over on our time a little bit, so that worked out perfect on the questions. I really appreciate everybody spending time with me today on this presentation. Again, if you go to the website, look for the Contact Us button to get more information. That way we can make sure you get what you need. If you use the Contact Us button, that'll also make sure that I can see that. So if you've got questions specifically for me, you can go through there as well. For example, if you have the elevated tanks and you have more questions about that, I can try to get some data on those to answer those as best as possible. If you're doing something special like spherical tanks and think that this is just the solution, again, I can work with you to try to come up with some answers on what you could do with that. I'm just not that familiar with those tanks at this point, so I don't have those offhand. But again, contact us. That's the best place to get started. And thank you very much, and have a great day.